Okay, so essentially when it comes to explicit schemes, the delta t has to be chosen such that things are stable. This is a really important consideration. Okay, we have to choose the delta t so that things are actually stable. And so explicit schemes can have very bad stability problems, and so the Courant-Friedrich-Levy condition is what we can use to try and assist us in what's going on. Now what it boils down to is really we want to make sure our delta t is less or equal to 2 over our maximum omega, maximum eigenvalue. Okay, so that eigenvalue, which as we know is radians per seconds, becomes 2 over, so 2 seconds, or 2 times as units seconds over radians. That's what this boils down to. But if my omega is very high, okay, then this delta t becomes very small. If omega max, my maximum omega for the mode that I'm choosing is very low, then delta t can be larger. This is what this tells you. How do we approximate omega max? So omega max we can go and compute actually from the system, compute the eigenvalue problem and see what the maximum one is. Or we can approximate it crudely by saying, if I know what the speed of sound is in my material, which I can compute from the Young's modulus over the density, the square root of that. That is a way to compute the speed of sound in that material. And the characteristic element length. So what is sort of the typical element length that I have. And then I can say 2c over h gives me an approximation to omega max. I can then use that to say, make sure my delta t is less or equal to 2 divided by omega max. And the cool thing is if you use a lump mass matrix system, this is why explicit always typically uses lump mass matrix systems, because it makes it very quick to compute the inverse of the mass matrix, which essentially is a requirement when it comes to some of these update formulas, which we're not going to go into detail now, but just want to give you a feeling. But also the lump one under predicts natural frequencies. So essentially what it means is if we under predict the natural frequencies, it means we can get away with a larger time step. So our natural frequencies are less than what they actually should be in the real life, but it allows us then to get away with slightly larger time steps. Okay, that's some of the rationale behind that. The implicit schemes on the other hand is when I choose beta 2 not equals to 0. So there's different choices you can make for that, to choose for beta 2 and beta 1. So if you make this choice, for instance, you end up with something that's called unconditionally stable. So it doesn't matter what your time step is. It doesn't mean it's accurate, it just means it's stable. It will compute. So I can make my time step 1,000,000 seconds, or 5 seconds, or 10 seconds. It will always compute something. It might be highly inaccurate, but it will at least compute. Okay. The other aspect here is when we use a diagonal mass matrix for the implicit schemes, there's usually no benefit of using a diagonal mass, there's no benefit for using any diagonalization of the mass matrix. So this is often why these systems typically might use sort of the normal full or the consistent mass matrix. Okay, that's really what it boils down to. But the reality is these are the two direct integration schemes. And what is important here is to take home is that there's a couple of things you can compute to help you guide what's going on. So I want you to be able to do this. I don't care if we're not going to implement this, we're not going to look at how to implement this. That's something you can explore in another finite element course. But what is important is that you're just aware of the fact that you have direct integration. You start at time 0 always, you integrate, that you understand that explicit, very small time steps typically. So explicit is used for crash simulations, explosion simulations, that kind of stuff. That's where you'll use explicit time, because by the time your time step is so small to capture that event, it's already accurate. And the implicit schemes are when you want to have larger stuff. But if you can get away with doing sort of a modal approach, there's huge benefits. It's very computationally efficient, and you can evaluate at any time what the responses are. So highly, highly desirable in that regard. Okay, so that's really what that boils down to. I'm not going to talk about numerical damping at all. I'm also not going to talk about Euler Bernoulli beams. That's stuff that are not that difficult, and that's really the end of this section here. So please make sure that you just take your time, read through this on your time through this sort of semi-discrete equations of motion, and really focus on this free vibration side, and also on this sort of direct integration side. I just want to make sure that you understand what is that there are these sort of three thoughts of school: modal approaches, direct, implicit, direct, explicit, and that they have huge consequences in the time it takes to get to a solution. So what I'm going to do is showcase tomorrow using a code, if I get the code to run, to showcase some of the responses that you would get from these different approaches. Okay, so that really concludes sort of what we're going to be doing in the dynamic side. So what I want the take home is from this material is that you are able to appreciate how to compute what's involved in computing sort of the mass matrices. So you should be able to do that for the 1D systems, no problem. I want you to be able to do that. If I would supply you with a mass in a matrix and a stiffness matrix, that you're able to compute the eigenvalues and eigenvectors of that system, either following an approach like this, or via sort of maybe some built-in generalized eigenvalue solvers. And then largely just to understand that there are modal approaches to solve a problem, what the benefits are, what is the benefits of and then the direct integration approaches, what is the sort of the difference between explicit and implicit schemes. So implicit, it takes a lot more time per time step to solve, but you get away with larger time steps. Explicit, cheaper to solve per time step, but it requires lots of small time steps because it's got some stability issues. So again, explicit, explosion, car crashes, that's what you want to solve there. Implicit is sort of for stuff that requires you to go a lot further into time. When you have to get at 100 seconds, you can't really get there with explicit schemes. Typically, you need to then use implicit or the modal approaches. And hopefully this wraps it up for you and connects this a little bit to what you've seen in your vibrations course, so that you can relate and say, this is how I get stiffness and mass matrices. Now, actually, once I've got the stiffness and mass matrices, I'm actually in vibrations. Then I'm in the vibrations course. Then I'm actually done with the finite element side, because all of this kind of integration and modal approaches are really stuff that you've sort of explored deeply in the vibrations side of the course. Okay, so hopefully that gives you a good round of how this material assists you in maybe extending what your knowledge is in vibrations to more complex kind of problems.